Okay, hi everybody. So, I guess the first time I heard about the Newton Institute was 11, 12 years ago. So my friend Matthias Aschenbrenner, who perhaps some of you know as co-author for one of my books, so he was here like at some workshop, and he told me about like some seminars I had. So that is some seminar program running on real algebraic geometry, whatever nonsense, and that is nice seminar. And suddenly they get interrupted. The door opens in the back, and in walks Prince Philip, followed by the Queen. So.
I'm sorry, Stefan.
No, I saved. I even saved just to be prepared.
Other way around.
No. Okay, so here's no. Okay, so here's my quiz question. So the quiz question for the non-British people is, why is it odd that Prince Philip comes in first? And for the British friends, the question is, why was it not odd for Prince Philip to walk in first? Okay, now let's see who knows his House of Windsor, or as we say in Germany, House of Sachsen-Coburg history. Okay. So let's see. Okay, so whatever I say today, which is correct, is joint work with Wolfgang L, Kevin Schreve. Actually, I never quite know how to pronounce him. I always pronounce it the German way, but Schreve, I don't know. Actually, never asked him. And Stephan Tillmann. Okay, so how about the following question? So let f of x, y be 2 plus 3 y plus pi x squared y squared plus e x cube y 4 plus, I don't know, plus say a, whatever a is, I don't care, x to the 5y. So let's consider that polynomial, and the question is f of x, y reducible? Okay, reducible meaning can you factor this as two non-trivial polynomials? Okay, so it's a more or less random polynomial. Hopefully it's random. So you would expect that it is irreducible. And then you can ask, okay, how can you show the quickest way possible that it is irreducible? Well, there are various ways of doing it, but somehow we're mathematicians, we want to do it the least painful way of doing it. The least painful way of doing it, which does not involve just plugging it into a computer. So here's one approach which I like. So we can, given such polynomial, we can look at the Newton polytope. So let me remind you what that is. So definition. So given f of x, y, we define so p of f. So p stands for polytope. And what it is so let's say, so I have to say what is so let's say what is a polynomial. So it's aij x to the I, y to the j. We define, okay, so what we do is we look at all ij such that the coefficient here is non-zero. So that is a subset of Z2, and then perhaps you take the convex hull. Okay, so then that is a subset of R2. Okay, so what does that have to do with our question here? So note, so little exercise, that the polytope, taking polytope is multiplicative, or multi-additive, no. Anyway, so if you have like a generalized, you have two polynomials f and g, then that is just, the polytope is just the sum of polytope of f and polytope of g. I have to tell you what you mean by sum. So here It's called Minkowski sum. And what is that? So the simplest thing you can think of, namely, it's just all points in R2, which you can write as a sum of a point in here plus a point in here. So that is, so it's all points that form X, or I already used X and Y, that's bad. V and W, where V is point in the first polytope, and W is a point in the second polytope. Okay, Minkowski sum. Again, that's, I'm using little exercise, not very hard. And so if you want to show that a polynomial doesn't affect them, then one way of doing it is to say, you look at the polytope, and then you show it it's not reducible. You cannot write it as a sum of two polytopes. So here, so if I go back to my example, okay, so let's see, what do I have? Okay, so let's see, so x 0, 0, y, I should not use green, should I? Oh well, too late. X square, y square, x cube, y to the 4, x to the 5y, okay, something like that. So that is your Newton polytope, and now it's an amusing exercise to a very finite exercise to show that you cannot write that polytope as a sum of two polytopes with integer vertices. Okay. So if you do the exercise and you realize actually you can factor it, which is not supposed to be, then so if you disprove me, trust me, I always have alternative facts for you. Okay, so I can always handle it. There's always a concept of alternative facts nowadays. Anyway, oh, I forgot. Okay, sorry. I just realized it's actually a topology conference. Somehow I was in the algebra conference mode. Okay, sorry. Okay, so let me talk about the manifolds now. Sorry. Okay, so sorry. I apologize. Okay, manifolds. Sorry, manifolds. Low-dimensional topology. Three manifolds. Okay, sorry. Okay, sorry. Forget about it. Okay, so let n be a three manifold. Okay. So polytopes. How about the good old Thurston norm? So let me remind you. So given a phi in h upper 1 of nz, which is the same as h lower 2. So if you're like me and you're cohomology phobic, then you also run to homology as quickly as possible. So we define the xn phi. Okay, so what is it? So we can always represent any class in H2 by an embedded surface, and then probably embedded surface, and now you want to take the minimal complexity of such a surface. Okay, so here minimal complexity. So we look at all surfaces properly embedded in N, such that sigma represents phi. And okay, now we want the minimal complexity. Okay, what can we do? There's genus, but I want to allow this disconnected surfaces. So G is not so good. So better to perhaps work with an Euler characteristic. Where we want complexity. Complexity should be non-negative. Euler characteristic tends to be negative. So how about minus Euler characteristic? Let's see. Minus Euler characteristic. But now you see, if you want to minimize that, that's also not so good, because you can always just take your surface and you attach, like you add a trivial S2 component, and then that goes down. That's kind of annoying. So what, let's say sigma hat means you take your sigma and you kick out all spherical components and all disk components. Okay, so here, so that is sigma minus disks and spheres. Okay, so you remove all disks and spheres, and what you get, you take a minus Euler characteristic, and that's my complexity. Okay. So I'm using exercise is to show that that is actually a semi-norm. So first of all, it has a triangular inequality. That's more or less obvious. So you take a phi1, phi2, take two surfaces, sigma 1 and sigma 2 of minimal complexity. Then you take the union of these two surfaces. Of course, they might intersect, but we only want to look at embedded surfaces. But then when they intersect, you do a little cut and paste argument, which does not change the complexity to get an embedded surface. Okay, of course, it might be lower, but that's how you show the triangular inequality. So, and an amusing exercise using a covering theory, which I always forget how it works, is that is actually homogeneous. K times x and phi. Okay, that's an amusing exercise. Okay, so that means xn is in fact a semi-norm. So it can be certainly can be 0. Take a 3 torus, then you can always represent any class by a torus which has complexity 0. So it's a semi-norm on integral cohomology. But then again, I'm using exercise. If you have a semi-norm on integral whatever, if you tensor with R, it still extends to a semi-norm. So this really extends to a semi-norm on the real cohomology. Okay, so this extends to a semi-norm. So either the chalk is bad or the blackboard is bad. Okay. Was that on video now? Okay. Okay. This extends to a semi-norm on, let's say, real cohomology, and of course, as everybody knows, that's called the Thurston norm. Okay, called the Thurston norm. Okay, now, okay, so it's norm, semi-norm, and okay, we all like pictures, so we also, at least I like, when I have an object, I want to see it in a picture. And how do you picture norm, semi-norm? Well, you do it by drawing the unit norm ball. So, so we define. So let me call it the Bn. So B is in ball. So it's the unit norm ball of that semi-norm. So it's all phi in real cohomology such that x and c is less equal than 1. And okay, so what is it? So here's now the picture. Okay, so here is some real cohomology, and for me all examples always have first bit number 2. Okay, so what is it? So if you have a semi-norm, if you do the norm ball, it is always going to be convex. So it's a convex subset by definition. But now what's much more interesting, and that's one of the trillions of things Thurston proved, is that what you get is actually a polytope. So you get a polytope. And actually it's symmetric, so by definition more or less. And now I have to draw a symmetric polytope, which, whatever. Okay, so it's symmetric polytope. And okay, so we have a couple of vertices, and what's also kind of neat is the vertices actually lie in a rational cohomology. Okay, so vertices lie in rational cohomology. Okay, that's pretty. Actually, so I was at some point looking at Thurston's paper, and okay, so he sort of gives a proof why it's a polytope, and then he refers to some of his earlier work. Then I guess I gave up reading. So if anybody knows like a more modern account of that fact, let me know. Well, I would not mind understanding that a little bit better. Okay, so in fact, now you could say the picture is a little bit misleading because I said it's semi-norm. So if you do the dual ball of if you do the norm ball of a semi-norm, what you get is a polytope, but it doesn't necessarily have to be compact. So it could also be, let me just draw a different picture. So for example, that would also be okay. So that would be for like if you take S1 times the surface for an exercise to show that the Thurston norm ball is actually some non-compact infinite strip. Okay, so we really like compact polytopes. So there's one last trick up in my missing sleeves. Namely, you can, if you don't like that polytope, you can always go to the dual polytope and hope for the best. So let me put it here. So we define. Okay, so that's just a general nonsense procedure. If you have one polytope, if you don't like it, here's an alternative polytope. And what it is so it's now going to be a subset of the dual space to H upper one. Anyway, I said I don't like homology, it's scary. So let's do homology much easier. So but think of a homology as a dual space of cohomology. And now what it is so it's all V in real homology such that CV is so equal to 1 for all V in that polytope. Okay, so the general nonsense procedure to go from a polytope in one vector space to a polytope in the dual space. Okay, so perhaps let me draw on one last picture. So okay, let me draw the one example where I can actually draw dual polytopes. A little bit tricky as an exercise. So let's say here we in H upper one, here in H lower one, and I have a basis here, and here I pick the dual basis. And now if let's see what we can get straight. Let's say you have a diamond here, and then the dual for an exercise looks like a rectangle. Okay, so that's an amusing exercise. And so here we had said the vertices are rational. So more or less by definition, the vertices here of the dual polytope are also rational. But now it turns out that Thurston has one last improvement on the whole story, namely, in fact, he showed that for the dual polytope, the vertices are integral. So these are here vertices lie in H1NZ, perhaps more torsion. Oops. Okay, and for our Heegert-Fleur friends, so as if I understand correctly, if you have a closed manifold, that is just if you want a Newton polytope of Heegert-Fleur homology, if I understand correctly. Again? With whatever coefficients, with whatever decoration, yeah. Who cares? Okay, anyway, so that's kind of fun. So let's see where. Here's an iteration. Okay, so that's kind of fun. I wish I had one more complaint, one really big blackboard. Okay, so I guess now I have to, oh, yeah, it's going to be a mess. Okay, so these two blackboards here are supposed to be one big blackboard. Okay. So, so what do I want to do? So what I would like to do is I would like to associate them to topological space polytope. Why not? Okay, so let X be topological space, perhaps a CW complex, and perhaps we'll have a few more adjectives later on, but let's just start here. And what I want to do is I want to start here with X, and I want to end up here with polytopes. Polytopes in, or perhaps integral polytopes in some suitable space. Okay, so that's the goal. We want to go from our X to integral polytopes wherever. Okay, so here I'm pretty general. X is say a CW complex, so no fancy methods. So the only thing you basically have at hand is like a classical algebraic topology. So what can we do? So okay, so I guess we go to perhaps some chain complex, cellular chain complex. Now, okay, perhaps we want to get some maximum information which is available. So perhaps we look at the chain complex of the universal covering. Let me put here X tilde. So that is the universal cover. Okay, that's almost the bigger, like the object with most information. Well, okay, we're ignoring a cup product. And okay, so what is that as an object? Okay, the chain complex. Chain complex, of course, over the integers, but it has a little bit more structure. So you have the fundamental group of pi1x acting on X tilde. So what you have here is, in fact, a chain complex over the group ring of pi1 of x. So perhaps let me call pi is pi1 of x. So that is a chain complex. Chain complex of so let's see z pi modules. Okay, so z pi is in general non-commutative. So then you have to be a little bit careful what you mean by module. So it's really, if you think about it, it's really a left. You really have left multiplication. So it's a left module. So pi1 of x. If you think about the action on the universal covering, it's a left action. So it's really a left module. Okay. Okay. So where possibly could we get a polytope from? So let's see. So how about since I already started off the wrong way with the Newton polytope nonsense? Perhaps let's see. Perhaps it helps us. So if we have a multiple polynomial, we get a polytope, and in some sense the same procedure also works for group rings. So for example, like here you have a map. So z pi perhaps minus, let's remove 0. So here's a map. So what you do is, what can you do? So take an element in the group ring. So what does that mean? So that just means, so here, it's a formal linear combination of elements g in pi. So to such an element, we can associate a polytope. So what we do is we basically do exactly the same as before. We look at all the g's such that the coefficient is non-zero. So here, so G such that a G is non-zero. Let's see what else do we do here. Okay, so convex hull, so they have to lie in some vector space. Well, okay, you could take the vector space of spanned by all G's a little bit big. So perhaps what's nice is if so we can always go from pi to its abilization to first homology. So let's say here integral polytope in h1 pi with let's say real coefficients. And so what we do is so we take our G which sits in pi, and we consider the corresponding element in first homology. So perhaps so here so that's supposed to be so that's supposed to be in h1 pi r, and here okay. So is everybody right for sitting in the last row? Here's lots of space. So here we go, same here now, convex hull. Okay, so we do almost the same construction as before, just that perhaps we don't look at G on its own, but we look at the G's with non-zero coefficient, and then we go to we look at its image in first homology, and then we get lots of points, so hopefully in first homology, and then we take the convex hull in first real homology. Okay? Okay, so to any element in a group ring, you can just assign a polytope that way. And so here, for example, like if the group pi is just a Z2, then you get, it's exactly the same construction as before. Okay, so so let's see, so we start here, so at x tilde, and we have this brilliant idea that if we have an element in the group ring, then we get a polytope. Okay, so what we should try to do is we should try to get from the chain complex here to an element in the group ring. So that would be nice. Okay, so if we have a chain complex of R modules, and we want to get an object in R. Okay, so you flip through your favorite algebra topology books, and then at some point you hit on the concept of Reidemeister torsion. Okay, so so what's Reidemeister torsion? So it's a conventional concept. If you have a ring R, you have a chain complex of R modules, which is acyclic, then the machine spits out an element in R. That's Reidemeister torsion in a nutshell. Like, you have a chain complex of R modules, it's acyclic, but your chain complex is based, so it has, like for each C star you have a preferred basis, then it spits out an element in R. Okay, so that's a Reidemeister torsion. So what you need is, you need an acyclic complex. Okay, so let's see. So here we have that complex here. Let's check whether it's acyclic. First theorem of homology theory tells you that H naught is never zero. Okay, so that is certainly not going to be acyclic. Okay, so you have a chain complex which is not acyclic, but you want the chain complex which is acyclic. Okay, one thing you can try to do is, like if you have a chain complex over some ring R, you can always tensor with the quotient field or a quotient field of R to somehow make it more acyclic. Okay, so that's going to be our idea. So we take that chain complex, not acyclic, but perhaps if we tensor it with something else, perhaps it then becomes acyclic. So, okay, so here, okay, so let's see. So here that pi, and now let me write here k pi. What's k pi? Okay, so k is supposed to be as in Körper field. So what I would like k pi to be is a quotient field of the group ring Z pi. So let's see, perhaps I put it on that blackboard. So let's see what that could possibly be. Okay, so okay, now I have to tell you what is the k pi. So where okay, so we have a group of pi. Let's say so I want to get I want to have a notion of a quotient field for Z pi. So perhaps you want pi to be torsion free somehow. If you think about the group ring of a group with a torsion, it's not a domain, so it's not going to have a quotient field. So let's say pi is torsion free. Okay, so okay, torsion free group. Okay, let's do the baby case. So if pi is abelian, then that's easy. Okay, so then pi is just a z to the m. The group ring of z to the m is just Laurent polynomials in T1 to the Tm, and then of course you have a quotient field. Okay, so it's so if pi is abelian, then that is just so here so that would mean it's z to the m. So then let's just say it's q T1. So it's a rational functions in T1 to Tm. Okay, so that's good. Okay, now unfortunately, so say if you want to do a 3 manifolds, fundamental groups of interesting 3 manifolds tend to be awfully non-commutative. So what do we do? Okay, now again you flip around. It's like you don't flip around. That's old-fashioned. You go to Google and search a quotient field group ring, and so then what you find out is okay, so what's the quotient field anyway? So if you do like if you teach algebra, well, it's sort of like you have a domain, let's say commutative, then you just write down like formal quotients, and then you define the addition, and everybody's happy. Okay, now you can ask why not do it if the same way if pi is non-abelian? And it turns out the same approach works with a little bit of effort. So you can define like a given pi, look at the group ring, you can define sort of like a relatively naive quotient field almost the same way as you would do in algebra. If pi is, say, amenable. So there's the name is called it's called Euler localization. Euler localization. So if pi is say amenable. So if your group is not too big, so okay, if you're like me and you never know what's amenable, just think solvable. So if your group is relatively small, then it actually turns out you can make sense of getting a quotient field as in the abelian case with a little bit of extra work, but fun exercise, but you can do it. Okay, so Euler localization is really just like a naive quotient field where all elements are naive fractions. Okay, so it turns out that it's never ever going to work if a pi is non-amenable. So for a free group, it's just not going to work. And since in particular we want to do a 3 manifolds, so fundamental groups of 3 manifolds tend to be non-amenable. If you're not aware of that fact, there's a great book by Wilton, Aschenbrenner, and somebody else, which explains it in great detail why 3 manifold groups tend to be non-amenable. Okay, so we have to deal with the case that pi is not amenable. Okay, and now okay, now comes the big gun, which I learned from Wolfgang L. So okay, now here comes the big gun. So here there was 1, 2. Okay, so if also in general case, so if okay, the general case, and now okay, now we need okay. So let me first write down what we do. So okay, so let's see. So we have the z pi, And then there's something called the von Neumann algebra of pi, of z pi, whatever that means. It's like a bounded operators on L2 of pi, which commute with left or right action of pi. Okay, it's a big gun. In something that doesn't really matter. But okay, if you think that's bad, it gets worse. So what you can do is, so from there, you can, so that's a ring, a monstrously large ring. And now you can actually invert all non-zero divisors. So here you actually can now play the fun algebra games again. So here n pi, and you invert non-zero divisors. So zd is zero divisors. Okay, so that actually makes sense. Don't ask me for details. But here you have a monster. And now what you can do is you can look at, I should not use green, we were saying, purple is better. So in here, you can look at the division closure of z pi in here. So let me call it division closure of z pi. So, and that's called the k pi now. Okay, so what does it mean? So, so division closure is quite simple. So, okay, here you have a monster, which I don't expect you to understand right now, because I don't understand it either. But here, so here you have a monster. Okay? So you have a ring here, you go to that ring here, and the division closure just means, let's see what I get straight. So you take the smallest, okay. That's right. So you look at all elements which become invertible here, and then you take the smallest subring of that ring, which makes everybody, which makes all these guys invertible. So you take this. Let's see. Okay. So you look at all elements in here which become invertible in that ring, and now you take the smallest subring here, which makes exactly these guys invertible. It has nothing to do with that situation. So you have a ring homomorphism from R to S, and the division closure of R and S is just you take so some guys from R become invertible in S. Now you take the smallest subring of S, which makes all these guys invertible. So division closure is really harmless. It's just that here you have a monster. Okay, now you can define all kinds of things, and of course you can define that. The question is, do you get something reasonable? And it turns out if pi satisfies the Tier conjecture, Tier conjecture. So what is a Tier conjecture? So it's something about integrality of L2 Betti numbers. Supposedly it holds for all torsion-free groups. It holds, for example, for almost all 3-manifold groups. The reference is in this fantastic book by Wilton, Ashman, and somebody else. So it's a big conjecture. It's been established for reasonable number of groups, but the status is perhaps in general perhaps somewhat unclear. But it works for almost all 3-manifold groups, which is good because we like 3-manifolds. And the reason why it works is that the proof goes through the virtual fibering conjecture, or virtual fibering theorem. Somehow one knows that the Tier conjecture holds for free groups. It holds for extensions of free groups by amenable groups, so which means it works for surface groups and also for fundamental groups of fiber 3-manifolds. But also you can always extend by finite groups, so it also works for virtually fibered 3-manifolds, and almost all 3-manifolds are virtually fibered, as we now know. Okay, so it's a big gun, but it works in the setting we perhaps care about. Okay, and what's so good about the T conjecture? So then it's a theorem, I think, of Linnell, or perhaps Luc and Linnell, that in that case, K pi is in fact a field. So a priori it is what it is, but it is a field if pi satisfies the T conjecture. So a skew field, perhaps to stress a skew field, if pi satisfies the T conjecture. Okay.
So in particular, it's not necessarily commutative. Is that what you're saying?
Say again?
It's not necessarily commutative.
Oh, it's certainly not commutative because so here it's really so that pi is non-commutative in general, and it's really so it's really embeds into that field. Yeah, so it's not a quotient field in the sense like not every element in K pi is like you cannot write every element as a quotient. So it's a much bigger, but it is a field which contains a group ring. Okay, so that was a long story. Okay, so now we have a chain complex over this field K pi, and now you can ask whether it is a cyclic, and as we all teach in algebra topology, there's a very simple abstraction to something being a cyclic, namely you just look at the Euler characteristic. Okay, so if Euler characteristic of x is non-zero, whatever you do, it's never going to become a cyclic. Okay, so it's certainly not going to work for all x's. So for which one does it work? Well, okay, let me just write Euler characteristic of x is 0, even though we'll quickly supplant it by something which is somewhat stronger. Okay, so with this chain complex, now Euler characteristic is 0, so we have at least hope that it becomes a cyclic. And I guess another theorem of perhaps Linnell and Luc is that that is a cyclic if and only if the L2 Betty numbers are 0. So so L2 Betty numbers are 0. Okay, now perhaps if you don't like L2 Betty numbers, so for example, like it's I guess Singer conjecture perhaps. So if you have an odd-dimensional manifold which is aspherical, then the L2 Betty numbers should vanish. So for example, like think 3 manifolds, think aspherical 3 manifold, its L2 Betty numbers are 0. So that's a theorem of, I guess it was safe to say Luc and somebody else. Okay, so it's not, in most cases, or like if Euler characteristic is 0, if whatever you stare at is aspherical, you have to be awfully unlucky for your L2 Betty numbers to be non-zero. So you shouldn't worry too much about it. Okay, so so that means a cyclic. Okay, so that means we can look at its Reidemeister torsion. Let's see. Getting nervous here about my space. So okay, let me put it here. So tau stands for Reidemeister torsion, and here K pi Z pi. Okay, so you pick up the fantastic little green book of Thuraev or Milner's fantastic notes on white torsion, and then it says if you have an acyclic based complex, and the basing here just comes from XOCW complex, X tilde was universal covering, and then for each cell downstairs you pick a lift upstairs, and that gives you an almost canonical basing of that chain complex. Okay, so you get Reidemeister torsion. Now the question is, where does it actually live? What is it? So okay, so it lives in K1, K pi. Okay, so in general, if you have like if you whatever ring here, R, and you have an acyclic base chain complex, the machine spits out something in K1 of R. Now, what is K1 of R? In some sense, it doesn't matter. In general, like if you have a general ring, it's a frightful mess. But if your ring is a skew field, then in fact it turns out to be something quite straightforward. So what it is you take K pi, perhaps some non-zero elements. So you take non-zero elements in K pi. That is a group under multiplication. And so if you have a group, you can always abelianize it. Okay, so that means you take K pi minus 0. It's a multiplicative group, and you abelianize it. Okay, so and that okay, perhaps I should say quickly about that isomorphism. So the point is, so K1 is basically just K1 of some ring R is basically just invertible R matrices over R of arbitrary size, sort of, and then this isomorphism here is determinant. What is determinant? Well, if you have now a matrix over skew field K, what you can always do is you can take your matrix and you just diagonalize it using row and column operations, and then you take the product of the guys on the diagonal. Now, if your field is non-commutative, you really have to worry about whether that is well-defined or not. Well, it turns out in general it's not well-defined. That's why you have to look at it, where you have to abelianize the way you go to. So up to abelianization, turns out it is actually well-defined, and it turns out it's an isomorphism. Okay. Okay. So we said if we have a non-zero element in the group ring, we can associate to it a polytope. Unfortunately, we did not end up in the group ring. We end up in something different, namely with K pi abelianized. Okay. So, okay, now let me perhaps cheat. So I was just saying before that elements in K pi are in general not quotients of elements in Z pi, but let me just tell you what to do if what you have here is in fact a formal quotient of elements in Z pi. So let's say we have here a quotient P, Q inverse, such that P and Q are in Z pi minus 0. Let's just say we have such an object. And we really like polytopes. So what can we do? What can we do? So perhaps okay, perhaps I should talk for a second about polytopes again. Okay, so we have polytopes, and we saw in the beginning that on polytopes we have an operation, namely Minkowski sum. And that works, makes sense for polytopes in whatever. So so if you look at integral polytopes in whatever, that is actually a monoid under Minkowski sum. So that is in fact a monoid. Okay, and Z pi minus 0, well, it's also a monoid under multiplication. We wrote down a map from one monoid to another. So that's also a monoid. Okay. So we wrote down a map. So we saw that for pi equals z2, that map was in fact a monoid homomorphism. There was a whole thing like a polytope of f times g is polytope of f plus polytope of g. And now of course you ask, well, sounds reasonable that that should be a monoid homomorphism in general. And if you had done the exercise from before carefully, you would have noticed that at some point you use the following convenient fact. Namely, if you take two non-zero integers, the product is still non-zero. Okay, so but at some point you used it. And so it turns out if you want to show that that is a monoid homomorphism, what you need is that you have the same statement in Z pi. You want Z pi to be a domain. And fortunately, that is, well, another conjecture. Kaplanski conjecture says that if pi is torsion free, then Z pi is a domain. It's one of these nice conjectures in group theory. And okay, so proof for all groups. But here, in some sense, I was here using a bigger conjecture. If you give me a group for which you know the Atiyah conjecture, we also know the Kaplanski conjecture. So that is a monomorphism, a monoid morphism. But I just write morphism. So okay, there's a so morphism if well, if your conjecture holds, but it certainly holds whenever that holds. So there's nothing to worry about. Okay. So what does it mean? So if we have two elements P or F and G in your group ring, then you can form polytope PF, polytope PG. And then P of F times G is polytope as P of F plus P of G. Now, unfortunately, here we don't have F times G, but P Q inverse. So what can you do? So you can form terrible notation now. So okay, so that's a big curly P, whether that is a tiny cute P like this one here. And you can form the big curly polytope of Q. Okay, but now here you have inverse instead of, so perhaps you want to put a minus sign here. Now, okay, what should that mean? Minus sign. Well, so you have this, we said polytopes form a monoid, but then you can always turn a monoid into a group using the usual construction. So that lives, it doesn't live in polytopes, but it lives in the, well, if you want a group of polytopes. So here you have a map to, well, sometimes called a Grothendieck group, because everybody likes to say Grothendieck, sounds fancy. But Grothendieck is just like, we have a monoid, you turn into a group, and it's called Grothendieck construction. So Grothendieck group of polytopes. Okay, so okay, so in this setup here, so if you have a CW complex, L2 numbers will vanish. Let's say just all characteristic is 0. Pi 1 is torsion free. You believe one or two conjectures, then you can assign to it a formal difference of polytopes. Okay. So it's kind of nice because it's like a totally general construction. Okay, now a couple of questions. One is, can you ever calculate it? Okay, so here we have like, I just erased it, this monster of field. So let's do one example. Okay, so let's say X is, okay, right, like that. So what does it mean? So I have two generator, one related group, and X is a corresponding CW complex, which is the same as pi. Okay, and then we get the chain complex, so C2X tilde, C1X tilde, C0X tilde. And then that map is easy. That's just x minus 1, y minus 1. And the other map, as every knot theorist knows, is given by Fock's derivatives. So here, del r, del x, del r, del y. Most likely I forgot a minus sign somewhere. Let me put one here. Okay, and turns out in that case you can compute the invariant. Why is that? Okay, so what do we ever use? Okay, so here at some point we had to calculate a determinant. I said take your matrix, which here boundary matrices are still over the group ring, and then we said, okay, we have a matrix over group over then a skew field, and then you just use row and column operations to make it diagonal. But at that point you have to do lots of inverting. That's kind of annoying. So the only case where it's really easy to calculate a determinant of a matrix is if your matrix is a 1-by-1 matrix. Okay? And it turns out here, if you think a little bit about it, then it turns out that the torsion is that 1-by-1 matrix divided by that 1-by-1 matrix. So here, so the polytope is the polytope of that element in the group ring minus polytope of y minus 1. Okay, so that's sort of the only case where we can sort of calculate it easily. The other question is, okay, so we have this polytope, and you can ask, what does it do for you? What does it say? So, for example, if I was just saying, that machine works whenever you have a 3 manifold. So theorem, so again with my co-authors, is if n is a 3 manifold. Okay, let's say irreducible and not a closed graph manifold. Then, okay, so we can form this polytope, which I guess, well, again, I never quite called it, but so P of n is what happens if you start here with n and you walk all the way to over there. So you get this polytope. Where does it live? So it lives in H1 n of r, H lower 1, I should stress. So, okay, you do this calculation, and you at the end of the long story, you walk into H1 of n with a polytope, and as you enter H1 of n with the polytope, you see, oh, there already is a polytope. So Thurston already placed a polytope there. And so, perhaps not surprising, Thurston always arrives there first. You get the Thurston norm polytope. Okay, so let me just last sentence. So if you have, for example, like as a corollary, if you have a 3 manifold and you're really lucky, you don't have to be lucky, that your pi 1 has 2 generated 1 related representation, then you can just determine our polytope easily, and then you automatically obtained the Thurston norm polytope. Okay, thank you.
Questions for Stefan?
Yeah.
So, in general, do you expect this approach to be easier to compute than
No.
usual?
But for example, like for us, since some group theorists sneaked into this room. So here's like a fun question. Take a 3 bicyclic group. So everything here works. So the machines, so if you give me a 3 bicyclic group, the machine spits out a formal difference of polytopes. And as we know, 3 bicyclic groups are sort of 3 manifoldish. So what does this formal difference of polytopes want to tell you? Or perhaps I would actually guess, by definition it's a formal difference of polytopes, but I would guess that for 3 bicyclic group perhaps it's just an actual polytope. So there's this polytope, formal difference of polytopes. For 3 manifolds it's the Thurston norm. What is it for 3 bicyclic groups? So perhaps that's a more interesting question. Like, you certainly cannot do any calculation. So that's the only calculation you can do, basically. But I really, really, really would like to know what is happening for, say, 3 bicyclic groups. Or what, like here also, like for 2 children in 1 related groups, you have this polytope. What is it trying to tell you? I don't know. Yeah?
Is there any way to extract any more information out of this element in K of pi star? Like, I mean, is it conceivable that you get a group at a vertex of the Thurston polytope out of it, or?
Well, okay, so if you have, let's say here pi is 3 abelian, then what you get is, well, like a randomized torsion, multiple Alexander polynomial, whatever you want to call it. So then, of course, you have more information than just the Newton polytope, but as you said correctly, as the corners, like you have lots of interesting information. But I think here it's extremely hard to extract anything. So I mean, I thought about it a little bit. So for example, like, okay, if pi is abelian, okay, no problem. If pi is amenable, then that is a little bit like what Tim Crocker and Shelley Harvey did. They looked at these Alexander polynomials with non-commutative coefficients, but the only thing they could ever extract was basically the degree of the polynomial. Like they never, I also thought about it, like you could never quite make sense of what should it mean, like the top coefficient of a non-commutative Alexander polynomial. So it never quite, we never managed to extract anything useful out of it. So in principle, there should be more information, but I think it's almost impossible to extract it from it.
Well, let's feel sorry for Prince Philip and the Queen for missing Stefan's excellent talk. Thank them very much.
Okay.